Hi everybody. Today we are covering section 5.4 in our statics textbook, and the topic is centroids or centers of gravity of three-dimensional objects. So we've already talked about locating the centroid of a two-dimensional plane object, and now we're moving on to extrapolate this discussion to a three-dimensional body. So as you can imagine, if we have this potato, it used to be just a slice of a potato, but now it has depth as well. The depth may not be the same everywhere, and the density may not be the same everywhere. So there's going to be a three-dimensional location for the center of gravity. And when we start talking about the weight, we can distribute it in this way. So if we have an x bar times the weight, a y bar times the weight, and a z bar times the weight, all of which would be equal to that coordinate x, y, or z, dw, and then integrate that content. Now, if it's homogeneous, that means if the weight distribution is equal everywhere, the density is the same everywhere, we can write it in terms of volume. So the difference between the first, which is we're talking about weight, and the second equation where we're talking about volume is if and only if our density is consistent throughout that shape. So there's no heavy spots, there's no light spots, there's no holes in it. Everything is homogeneous throughout. There are some common three-dimensional shapes and the location of the centroid of those shapes. And once again, I want to stress we're talking about centroids because this eliminates the idea of density distribution or weight distribution from the conversation. So we're talking about the geometric distribution. Now, there are other distributions that you can determine based on symmetry, because once again, when we're talking about the volume, if you have enough symmetry, for example, on a pyramid, if there is enough symmetry from one side to the other, you can make a determination that anything that bifurcates that a line that bifurcates that is going to be the location of the centroid. So here is a composite body, and rather than being integrated, or we could use the tables for this, which in your textbook, that table for those three-dimensional shapes is on page 276, right? But here on this slide, we're talking about a composite body. Basically, we have an angle. Maybe this is made out of iron, so maybe this is a corner brace, or maybe it's a shelf, or turned upside down, turned clockwise in the direction on the z-axis, or something like that. But basically, we have two holes, and we have a semicircular plate, a quarter circular plate rather, and then a rectangular plate from which those holes are cut. So we take this as a composite. We have that plate plus the quarter circle plate minus the two holes. And so we can use that kind of information to determine where is the center of gravity. And we can do that using the same sort of a chart that we used for finding the center of gravity in 2 dimensions. Except for this time, instead of using area, we use volume. And here it's sort of it's not actually a trivial conversation, but the thickness of this bar is the same throughout. So the location of the centroid is going to be the same as it would be in a 2-dimensional object, although since this is coming outward, that's going to change that conversation. So anyway, we use the tables to find the centroid of the quarter circle. We can tell by symmetry where the centroid is going to be located in the rectangular plate and the 2 round holes, remembering that the round holes, which are going to have negative volumes right down here, and the plate and the quarter circle are going to have positive volumes. We locate x bar, y bar, and z bar. Now remember, we have to locate that from a point, and I would locate that from the point 0, 0, 0, which is right here, which makes our y coordinates negative because they are below the axis. But just remember, always reference them from the same point. So the z-coordinates and the x-coordinates are always going to be positive. We have 2 negative volumes. We have 4 negative y-bars. So what happens here, where we have y-bar times the volume, those actually do become positive, and that is correct. So we add everything together to get our summation of volumes, our summation of x-bar volume, summation of y-bar volume, summation z-bar volume, and then of course we can divide the x-bar volume by the volume and come up with the value of x-bar, y-bar, and z-bar. So we locate x-bar at 0.577 inches, so it's just out this way. We locate y-bar is actually going to be a positive number, and z-bar is also going to be a positive number. So that's just an interesting result. I think this is incorrect. I don't like this. This should be a negative divided by a positive, so this should be negative. So it should be negative. I'm not sure if the value is correct either, to tell you the truth. Let me take a look. If we take a negative 5 point, trying to clear out my calculator here. Take a negative 5.047 and divide that by a positive 5.286. That value is, yeah, this is incorrect. This value is positive 0.9, excuse me, negative 0.9548 inches. So this value is incorrect. I will correct that on the slide and I'll post it up, but y-bar is negative 0.9547 inches. All right, so when you refer to this on our Moodle page, you'll see that I've corrected that value, and everything else works according to Hoyle, so we should be good to go. And ladies and gentlemen, that's it for Chapter 5. I'll post a few more problems, and on Wednesday we'll spend some time talking about your homework. Thanks, and have a wonderful day.